Today's lecture is going to be on the pressure, temperature, and components of the Earth's atmosphere. Where does the atmosphere begin and where does it stop? As one rises in the atmosphere, pressure decreases, and we can see it here in this picture. As we increase in altitude, we decrease in pressure, which is measured in millibars. So as we were hiking up this mountain, the pressure around us would change. Standing at mean sea level, one experiences more pressure than standing at some elevation. This should make sense because there's a larger column of air above one's head. But pressure does not only exist downward, it also exists horizontally too. Imagine standing in water, a fluid. The pressure exerted on your body is in all directions, not just downward on your head. Air behaves like a fluid, so air pressure is inward in all directions. If I look back at the graphic, here I would see that 50% of all air lies below this altitude. And as I continue rising, notice the slope changes because now we've got distribution of the remaining atmospheric gases in a much more broad area. So pressure at sea level versus pressure on top of a mountain versus pressure at a very large elevation, right, 100,000 feet, you're going to see a slope difference, and the slope difference simply reflects that. It has more space to spread out. Fluid pressure, air and water, act all over a body in all directions, not only in that vertical column of air. Submerging an object in water or air has the same effect. So let's look at this picture. Pressure pushes in all directions equally, up, down, sideways, so there's no net downward force. From inside the body, right, the internal body fluid pressure pushes outward in all directions to balance the inward pressure, so you feel no pressure at all. Right? Generally speaking, we don't feel atmospheric pressure. It's just the way our bodies evolve. However, if I look at this picture here, the further I submerge an object, the greater the pressure is at depth. There's simply more pressure because there's more forces pushing and squeezing around it. When we look at atmospheric pressure, we're really talking about the force exerted by the weight of the air. The weight of the air at sea level is considered to be 14.7 pounds per square inch, or psi, 14.7 psi. Air pressure decreases with increasing altitude. And the units of measurement are millibars. Standard sea level pressure is 1,013.2 millibars, or we could say 14.7 pounds per square inch. Those are equal values. Along with pressure decreasing with elevation, temperature decreases with elevation or altitude in the troposphere. In the troposphere, temperature decreases as one moves upwards. The troposphere heats from the ground up. The temperature decrease is called the ELR, the environmental lapse rate. The thickness of the troposphere is not the same everywhere. It varies all over Earth. The divide between the troposphere and the stratosphere is called the tropopause. So we've got some layers here that I want to make sure we pay attention to. Temperature, measured here on the x-axis, decreases at elevation. Notice we get this relative stability just beyond the tropopause, and then it begins warming up. And we see it warming in and around the ozone. At this region, we have the maximum ozone layer. It's actually really a protective shield. In this case, above it, it actually warms up at a greater rate, up until the stratopause. We'll get into that here in just a few moments. So let's look at what's going on here. Temperature increases with elevation or altitude in the stratosphere. So why would increasing elevation lead to an increase in temperature? Well, let's go back to ozone, a component of the stratosphere. It absorbs incoming ultraviolet light and heats up. The re-radiation into space above it leads to the increase in temperature in and above the stratosphere. So we have two different thermal gradients taking place. In the troposphere, decreases in temperature up until the tropopause. And above the tropopause, we start moving into the stratosphere. We have a stable region, a warming region, and then a dramatically warming region. So what are the components of the atmosphere? What is in the air? It's more than just a gaseous mixture of nitrogen and oxygen that comprise 99% of the troposphere. There are major components. The composition of air is not constant and it varies from time to time. We'll look at water vapor, aerosols, and ozone, which we've already kind of mentioned ozone. In the graphic above, you can see that near the equator, there's more water vapor than the poles. Notice the red discoloration, red, yellows to greens, and to the dark blues. This is a result of warmer air's ability to hold more water vapor. Colder air can hold less water vapor. On average, equatorial or tropical locations are warmer, so they hold more water vapor than cooler locations. When we look at aerosols, we simply could identify them as particulates in the air that lead to cloud condensation nuclei. In order for clouds to form, they must have a condensation nuclei in which they form around. Aerosols are kept in motion within the atmosphere due to the constant motion. The kinetic energy of moving air suspends particulates. These include dust, sea salt, smoke and soot, pollen, and even microorganisms. Yes, even living organisms hitch a ride in particles in the atmosphere. So let's look at this picture here. We have different particulates that come from natural processes on Earth and unnatural, right? We burn at power plants, there are forest fires, there's dust and debris that's being blown. It's being suspended in the atmosphere from the energy within it, much like that when we looked at sediment or turbidity in moving water. But these particulates serve a purpose. One, they can scatter light, they can reflect light, but they also can become condensation nuclei. So aerosols serve as cloud condensation nuclei for cloud formation. You have to have a particulate in which water vapor can condense around. So here let's look at ozone, a safety shield protecting life from ultraviolet energy. Ozone, or O3, is a substance that absorbs dangerous UV light that would do damage to living cells, or life in general. It would actually alter its ability to replicate. It heats up as the incoming energy strikes it and heats the layer above it. Here's a nice picture graphic from a kind of a cross-section. The ozone layer filters out wavelengths of shorter than 320 nanometers, which would be damaging to life, converting it into heat, which is why the ozone is hotter than other parts of the atmosphere. Notice UVC is completely absorbed, where some UVB, 95% is absorbed, some passes through, and only a very little bit of UVA is able to pass through. Excuse me, a large amount of UVA passes through, only a little is absorbed. So let's apply what ultraviolet light does to humans, to us. Right? That's what sunscreen's about, UVA and UVB. Well, it leads to sun damage. Over time, sun's UV light damages skin fibers called elastin. The breakdown of elastin causes skin to sag, stretch, and lose its ability to snap back after stretching. Essentially, it loses elasticity. Although sun damage may not be evident when you're young, it catches up later in life. Nothing can completely safeguard someone from skin damage, but there are obviously precautionary measures to protect yourself from skin cancer. Limit your time in the sun, wear sunscreen containing zinc oxide, SPF greater than 30, wear a hat that covers your head and face, and wear long, lighter clothing to cover your skin. So let's make sense of UVA. UVA leads to aging, right? So the A, right, aging and wrinkling. And what happens here is it penetrates deeper into your skin. UVB leads to sunburns. So B, burns, A, aging. And this is actually more of a shallow tissue issue that is absorbed by your epidermis. So UVA penetrates deeper and does damage. UVB does damage on the surface skin, or your epidermis, your outer layer. If we look at this picture here, we see UV light shining on a cross-section of skin. We have melanocytes that produce melanin to protect the skin from UV rays. And if UV rays exceed what can be blocked by your level of melanin, sunburn results. All right, moving up to the next layer of our atmosphere, the mesosphere. Temperature, again, decreases with height. So if we look at the mesosphere, we see up a little bit higher. The mesosphere is the coldest region in our atmosphere. This layer is one of the least explored layers. So let's go back and look at what's happening with temperature. It's decreasing in the troposphere. It's warming again in the stratosphere. It reaches the stratopause, and then it begins cooling again. So these are just general characteristics of what's taking place here. We live our life in the troposphere. The stratosphere contains ozone, the protective layer. The mesosphere is where we would find different rockets are launched to. We find different clouds at this elevation. We find meteors burning up. We would see essentially this part of the atmosphere itself is actually quite large, but at the same time it's got its own purposes. And lastly, the thermosphere, the outermost layer of our atmosphere. Only tiny amounts of atmosphere exist here. This is why we find auroras occurring, where Earth's magnetic field redirects the solar wind and excites atmospheric gases into dazzling displays of colors, and we call these auroras. In final, last picture, back to the original picture I was showing you earlier. Earth's atmosphere is complex and unique. Today's atmosphere is the evolution of Earth and life processes. Life has changed the planet and held it relatively stable for a few minor fluctuations of oxygen levels for almost 500 million, about a half a billion years. The atmosphere contains layers that have their own purpose for Earth's stability.